Hi students, Professor Nugent here. In this video, we're going to prove the Gauss Markov Theorem. The Gauss Markov Theorem states, under the 5 multiple linear regression assumptions, the OLS estimators beta 1 hat through beta k hat are the best linear unbiased estimates. They are blue of beta 1. Really, we're looking at even the slope estimate, beta, the intercept estimate, beta naught through beta k. So for our proof, we're going to show that for any other linear unbiased estimator of beta 1 tilde of beta 1, that the variance of beta 1 tilde is greater than or equal to the variance of beta 1 hat. So the way we're going to set this up is we're going to walk through a few steps that come up with an estimator beta 1 tilde that is linear and that is unbiased. And once we have a linear unbiased estimator, then we're going to show that the variance of that estimator is greater than or equal to the variance of the estimator, the OLS estimator. All right, and this is all to show that the OLS estimator is the best linear unbiased estimator. And what we mean by best, we mean that it is the lowest variance among its class, and its class of estimators is linear unbiased estimators. Okay, so let's do that. The first thing we need to do is define a linear estimator, and then we're going to define that estimator. We're going to further define that estimator as unbiased. So we define an estimator as linear in the coefficients, like so. Beta 1 tilde equal to sum from I equals 1 to n of W1I times Yi. This estimator, beta 1 tilde, is linear in the coefficients. This W1I represents a function of the independent variables x1 through xk. Now we can plug in the equation for yi so that this is equal to the sum from I equals 1 to n of W1I times beta naught plus beta 1 x1I plus beta 2 x2I all the way through beta k xki plus ui. And what we can do then is to take the expected value of beta 1 tilde given x. This is equal to the expected value of this whole thing given x. And note that the W1I, it's a function of the x's. The beta naught, beta 1, beta 2, beta k, those are parameters. Those are not random variables. So the x's are treated as fixed in repeated samples. The beta naughts are parameters. So neither of these things are random variables, and so they can be pulled out of the expectation. What we're also going to do as we pull these things out of this expectation here is we're going to put the betas in front of the summation terms so that this is equal to beta naught times the sum from I equals 1 to n W1I plus beta 1 times the sum from I equals 1 to n x1I W1I plus all the way through beta k sum from I equals 1 to n W1I xki plus the sum from I equals 1 to n of W1I times the expected value of ui given x. I write this is the UI is the only random variable on the right-hand side. And the expected value of u given x is 0. So that term, this whole term, is going to disappear. Let's make our lives easy and just wipe that off the map. Great. Now what we're trying to do is to show that the expected value of beta 1 tilde given x is equal to beta 1, right? So we set up that this estimator beta 1 tilde is linear. In order for this estimator to be unbiased, then the expected value of beta 1 tilde given x has to equal beta 1. So how can we get this right-hand side to be equal to beta 1? Well, if the sum from I equals 1 to n of w1i equals 0, the sum from I equals 1 to n of w1i x1i equals 1, and the sum from I equals 1 to n of w1i xji equals 0 for j equals 2 through k, then what we're going to see is that this term gets wiped off the map because that's equal to 0. That the rest of these terms are also equal to 0. This is equal to 1, and the expected value of beta 1 given x is equal to beta 1. Right? So let's plug these values in so that this is equal to beta 0 times 0 plus beta 1 times 1 plus through beta k times 0, so that this is equal to beta 1. So we have defined an estimator that is linear, and we have defined an estimator as unbiased. Now we're going to use these characteristics of the function of w1i later on, because the way that we built this estimator is going to determine what its variance is. Okay. So we have our linear unbiased estimator. Now we want to compare the variance of that thing with the variance of the OLS estimator. Let's set up some more tools. Let's let R1I hat be the residuals from a regression of x1 on x2 through xk. Then it follows that the sum from I equals 1 to n of w1i r1i hat is equal to 1, because x1i is equal to r1i hat plus x1i hat, right? So if x1i hat is the predicted value from this regression, the predicted value plus the residual is going to equal the observed value. And the sum from I equals 1 to n of w1i x1i hat is equal to 0. So what we have here is that this x1i hat, this thing is the result of the constraints identified above or previously to make the estimator unbiased. This x1i hat is a linear combination of the x2 through xk, right? So the constraints previously identified that the sum from I equals 1 to n of w1i xji I equals to 0 for j equals 2 through k apply to this because the x1I hat are linear combinations of the j equals 2 through k. The R1I is the partial out part of x1 that is unrelated to the rest of this. And it must follow that if the sum from I equals 1 to n of w1I x1I hat is equal to 0, that the sum from I equals 1 to n of w1I r1I hat is equal to 1. All right, so we've come up with, we have our additional tools. We've come up with a linear unbiased estimator. We want to compare the variance of that estimator with the variance of the OLS estimator. So what is the variance of that estimator beta 1 tilde? The variance of beta 1 tilde given x is going to be equal to the variance of the sum from I equals 1 to n w1 I yi, right? Given x. And this is equal to variance sum from I equals 1 to n of w1I. Now we plug in the equation for yi, beta naught plus beta 1 x1I plus through beta k xki plus ui, close parentheses, this is given x. And observe that none of this stuff, none of these are random variables. None of these are random variables. And so they all come out. And we are left with the sum from I equals 1 to n of w1I times the variance of u given x. So we can write variance sum from I equals 1 to n w1I ui given x, which is equal to the sum from I equals 1 to n w1I squared times the variance of ui given x, which is equal to the sum from I equals 1 to n w1I squared sigma squared. Fabulous. We have the variance of beta 1 tilde given x. And recall that we have previously expressed the OLS estimators as beta 1, the beta 1 hat as equal to the sum from I equals 1 to n of r1I hat yi over the sum from I equals 1 to n of r1I hat squared, which implies that the variance of beta 1 hat is equal to sigma squared over sum from I equals 1 to n of r1I hat squared. So now that we have identified what our variances are, we can compare them. Stay tuned to the next video.